Hi, everyone, and thank you for viewing my presentation. My name is Ethan Bendau. I'm a PhD candidate at Columbia University in biomedical engineering, and I will be discussing our results on the modulation of cardiorespiratory activity in mice using transcranial focused ultrasound. Over the last 10 to 15 years, studies of transcranial focused ultrasound neuromodulation in humans and animal models have led to FUS emerging as a promising method for targeted, non-invasive brain stimulation. Deep brain stimulation, a precise but invasive method of brain stimulation, has been shown to modulate autonomic nervous system activity, such as blood pressure and heart rate. Temperature can be a powerful means to modulate brain activity due to changes in neuronal excitability with temperature, changes in blood flow in response to excess heat, and changes in cellular metabolism with temperature. With this in mind, we sought to attempt to leverage the thermal effects of ultrasound to cause focused low-level heating in the mouse brain in order to modulate cardiorespiratory activity. All experiments were performed in wild-type black mice anesthetized with sodium pentobarbital. During each trial, heart and breathing rates were monitored via ECG and a respiratory pressure sensor. In each mouse, a single target was chosen and sonicated 15 times at a single pressure for 60 seconds each, with 60-second cool-down time between sonications. We used a single-element FUS transducer run at 2 megahertz at a pressure of either 425 or 850 kilopascals. The increase in temperature was separately measured in vivo by inserting a thin needle thermocouple directly below the skull to assess heating at the skull-brain interface. We chose 2 targets for sonication, encompassing spatially distant and functionally different regions of the brain. The primary target included the thalamus and hypothalamus, which are implicated in regulation of arousal and autonomic activity, respectively, among other things. In particular, the focus includes the subthalamic nucleus, a site of autonomic regulation via deep brain stimulation in previous studies. The secondary control target was located 3 millimeters anterior to the primary target and is a motor-related region, including the primary motor cortex and the cauda putamen. We performed acoustic and thermal simulations in K-wave to characterize the pressure and temperature profiles throughout the brain. After applying the relevant physiological parameters to the simulation, skull absorption and perfusion values were adjusted to best match the in vivo thermocouple measurements, which were used then to determine the approximate temperature rise throughout the brain. At 425 kilopascals, very little heating occurs and is likely counteracted by perfusion. At 850 kilopascals, the thermal increase is between 1.5 and 2 degrees Celsius throughout the brain, largely confined to the focal volume. During each window of sonication, highlighted in the gray bars at the graph at bottom left, we observed dramatic changes in heart and breathing rate at the onset of sonication. This shows one trial at 850 kilopascals at target 1. In each trial, following the offset of sonication, rates return back to baseline values, showing that the effect is reversible. The heart and breathing rate responses were target and pressure dependent, with sonication at target 1 resulting in decreased heart rate and increased breathing rate, while FUS at target 2 did increase heart rate while only slightly increasing breathing rate. Low pressure was associated with small changes, and sham trials were included in which the FUS transducer was not coupled to the mouse head. We expect that even in the secondary target, changes in heart and breathing rate may occur naturally, as increased respiration and perfusion are natural means of maintaining thermal homeostasis in the brain. We hypothesize that the large differences in effect seen at the primary target is due to ultrasound focus overlapping regions regulating arousal and autonomic activity. It is important to note that the effect is present even in deep stages of anesthesia, during which the mouse does not respond to toe pinches. In conclusion, we have shown that continuous wave FUS can reversibly modulate heart and breathing rate in mice, which is possibly due to ultrasound heating. The long-lasting duration of the effect, combined with the application of continuous wave versus pulsed ultrasound, and in the context of previous studies showing FUS-induced thermal inhibition of brain activity using similar temperature increases as presented here, together support that temperature may play a role in the effect presented here. In the future, we plan to isolate the thermal effect by using laser heating and to reduce the FUS pulse repetition frequency and duty cycle to decrease the temperature change and isolate the mechanical effects of FUS. With that, I'd like to thank the Focused Ultrasound Foundation, all of the members of my lab at Columbia, the NSF and NIH for providing funding for this project, and you for your time. Please reach out to me with any questions. Thank you.